Hi everyone, my name is Gong. I am a PhD student from Harvard University. Today I'd like to introduce our project Microscope, the first diagnostic tool that can zoom into microsecond level events in network functions. This is the joint work between Harvard University and AT&T. Network function virtualization, NFV, has brought about a lot of benefits, like flexible deployment and easier development. But the success of NFV relies on good performance, because it runs in software. In real deployment of NFV, network functions suffer from performance problems like high tail latency, low throughput, and packet drops. Our survey with 19 network operators showed that many operators spend more than 12 hours on 10 to 100 NFV performance problems per month. These performance problems are hard to diagnose because it involves many parties and it is easy to blame each other for the problems. Here is an example of an NFV chain where the operator sees a long tail latency problem in the VPN. The first suspect is of course the VPN, so the operators blame the VPN vendor. But when the vendors diagnose the VPN by running it alone, they do not find any problems. Then the operators start to suspect that the user traffic is the culprit because we get high latency during a traffic burst at the VPN. But there is no traffic burst at the user end. Finally, the operator finds that a problem is located in the firewall because there is a misconfiguration in the firewall. In reality, things could be much more complex. When problems happen, there are always such blame games among operators, vendors, and users, and our goal is to identify the correct culprit network function and culprit flow for each victim performance problem. Performance diagnosis in NFV systems is a harder task than diagnosis in distributed systems. Traditional distributed systems focus on request latency, which is usually in millisecond level. But in NFV, we focus on packet latencies, which is usually in microsecond level. The requirement is much tighter, so many microsecond level events start to become impactful in NFV systems, such as CPU interrupts, cache misses, or traffic bursts. These microsecond level events make prior solutions ineffective in NFV. Prior solutions use time-based correlations. They assume that events happening in the same time window with the problem are root causes. But this assumption becomes invalid in NFV because of so many microsecond level noises. Let's use the previous example to show this. Here we show a timeline of different events in the above example. In the beginning, a misconfiguration in firewall is triggered at this time, and the VPN starts to suffer from long latency during this time period. In the meanwhile, there were also some irrelevant microsecond level noisy events. As we can see, the misconfiguration and the latency problem happen at disjoint time periods. In this situation, it's really hard to define a fixed time window size. If the time window is too small, we can miss such causal relation between the misconfiguration and the long latency. If the time window is too long, the time window could include a lot of different noisy events, which makes it hard to identify the correct causal relation. This example shows why diagnosis in NFV is uniquely challenging because of the microsecond level events. These microsecond level events bring three types of challenges. First, the impact of a microsecond level event can propagate over time and across different network functions. Besides, when we have many packets with performance problems and many microsecond level events as potential root causes, it is hard for operators to focus their limited time on the most critical problems. To address the challenges, we designed Microscope, which leverage queuing information for diagnosis. the queuing information is efficient in resolving the impact propagation over time and across network functions. In the previous example, the VPN suffers from long-tail latency problem. Microscope first performs local diagnosis in VPN by checking the local queuing information. The queuing information tells us if the processing rate is too low or the input rate is too high. A low processing rate means the problem is local to VPN, and a high traffic rate means the problem is propagated from upstream. In this case, Microscope then performs propagation diagnosis. This step also checks the queue information as different upstream network functions and identifies the upstream network function that makes traffic rate higher, which is the appropriate network function. Here is the architecture of Microscope. In the runtime, Microscope collects queuing data from the NFV, which could be used to identify victim packets and network functions, and then perform diagnosis. After collecting the data and victims, Microscope then performs offline diagnosis for those victims. The diagnosis consists of 3 steps, including local diagnosis, propagation diagnosis, and pattern aggregation. The local diagnosis resolves the challenge of impact propagation over time. Propagation diagnosis resolves the impact propagation across network functions. Pattern aggregation converts a long list of diagnosis results into a short list of causal relation patterns, which is output of Microscope. Here we show our main evaluation results. We compare the diagnosis accuracy of Microscope with that of Netmatic, which is a typical diagnosis system based on time-based correlation. We inject 3 types of problems for the system to diagnose, including traffic bursts, interrupts, and firewall misconfiguration problem. Overall, Microscope has much higher accuracy than Netmatic. This figure shows the result. The x-axis represents the cumulative percentage of victim packets, and the y-axis represents the rank of the correct cause for each victim packet. Let's look at certain points. This point means for 89.7% victim packets, Microscope successfully ranks the correct cause first, while for only 36% victim packets, Netmatic ranks the correct cause first. We checked the results from Netmatic and observed that Netmatic failed to find causal relations with a fixed time window because it usually misses the correlations with many noisy events existing in the same time window. For the rest 10% victim packets that Microscope failed to rank the correct culprit first, we manually checked the queuing data to see what was happening. Our observation is that for those victims, almost all of them is caused by concurrent noisy events. For example, when we inject traffic bursts, interrupts could also happen in the meantime in some network functions, which also contribute to the same problem, so that interrupts should also be a culprit. In summary, we observe that NFV performance is critical to the success of NFV, which means NFV diagnosis is very important. However, we find out that there are key challenges in diagnosing NFV, which is the impact of problems could propagate over time and across different network functions. Such key challenges could cause blame games between network operators, NF vendors, and users who send traffic. We propose Microscope, which leverages queuing information to understand such impact propagations. Our evaluation results show that Microscope achieves much higher accuracy than existing solutions. Microscope is the first tool focusing on microsecond-level performance problems. We expect that Microscope to be generically used for other large-scale systems as we get higher speed and lower latency. Thank you very much.
Hi. Okay. So there's one question. On Slack right now. So this is from Aditya Kela, who asks, other systems such as PerfSite, which was published in INC 2015, also looked at queuing information and performed chain-wide diagnosis similar to Microscope, and was wondering, like, how does this prior work relate to your design, or what is different, or what has changed?
I think the key difference is we mainly focus on microsecond level events that like a packet may suffer from long queuing latency, long queuing delay in some network function that causes some problems. And based on my understanding of the previous work, like ProfSci, like Mathematic and other systems, they mainly focus on some coarse-grained timescale events. Yeah, I think that's the main difference. And because we mainly focus on the microsecond level events, this could have a very lasting impact on for the problem. So we cannot definitely know the time the correlation on the time based on time of the cause and the final problem. Yes, I think that's my question. That's my answer. Thanks.
Okay, so you might actually want to look at the paper more closely because PerSite also focuses on NFs. So I don't think the time challenge is necessarily makes sense. So another related question by Inanjai is, so, you know, sure you have, maybe you need, like the real bottleneck in actually responding to a problem is on the operator side. It's a human problem. So I guess like the question that Anand wants to ask is, why does it matter whether Microscope is fast or not in diagnosing problems? So why does it matter if Microscope returns results in 1 microsecond or 5 seconds, given that operators will take 10 minutes to actually do anything?
Maybe the video does not show all the details, but what we are doing is not actually returning the diagnosis result in a very fast speed. What Microscope did is in the runtime it will collect the queuing data from all the network functions, and once for some time period, then the Microscope will take offline diagnosis. So that's the that's a step what Microscope did. So actually, we do not have such a requirement for like returning the result within a very short time. So.
All right, Junji. So let me first ask some of my questions, waiting for other people to ask other questions. So one question I have is what are the typical root causes of performance issues you see in NFV? For example, you mentioned that interrupt is a problem. I'm just wondering why an NFV can receive so many interrupts.
Because because NFV is running on the software, it's not the performance is certainly not stable than some hardware mailboxes. These are just some process running in the commodity servers, so the network function performance could be impacted by a lot of software factors like the CPU scheduling, some interrupts, and also because the software network functions could also suffer from resource contentions like CPU contentions, memory bandwidth contention, even for the EQ contention. So all these resources shared by those network functions, even with other applications also running the same servers. Yeah.
Okay. The second question I have is how much overhead do we have in recording this packet trace?
I see.
For example, how much CPU you have to burn, because these also may trigger resource contention on the CPU.
Yeah, this is a really good question. So ideally, we want to collect all the packet headers from all the packets in every network function, but it's really increased a lot of overhead. So in our implementation, we made a lot of compression techniques. You can refer it in the implementation section in our paper. So finally, we only dump 2 bytes for every packet, and the overhead is reduced for about 0.8% to 2.3% for the network function we're running. Yeah, that's my answers.
Okay, yeah. So we have a question from Wei Bai. He's wondering whether microscope can diagnose layer 7 NFs, which may change packet transmission behavior. For example, an NF that reassemble a set of messages and then transmit them in a burst.
Yeah, this is a really good question. To be honest, our current prototype could not deal with the network functions that change the some packet like the flow forwarding behaviors, like some TOS termination and some other similar network functions. I think this could be in our extended work. But even if this NF chain contains such network functions, we could still diagnose the performance problems before this network function and after this network function. Yeah.
Okay. So I think your do you imagine your technique to work for other network systems, for example, physical network, because you are essentially assuming you have a distributed nodes connected by queues, right? So the physical network or any virtualized network satisfies that criteria. Do you think it's gonna work broadly for other applications?
Yeah, certainly. Yeah, this is a really good question. Actually, we are also thinking about what the scope of our prototype could solve. Like, so in our paper, we only solve the NF3. We only solve the problem in NF3 scope. But if we could also collect all the queuing data, queuing information from other network elements like switches, like from the hardware NICs, if we could achieve it, could collect all this information in a lightweight, we could also make these network elements as a node in our diagnosed graph. Like I think this will certainly be generic useful to other network elements.
Yeah. So one last question. This question is from Dongsu. Do you think you can leverage performance prediction, as what we have seen in the last talk, and combine it with your queue-based diagnosis to better manage NFVs?
Yeah, I think this is a very good question. Actually, to be honest, we have not think about this question because we are only focused on the diagnosis part. But actually, from the last talk, actually some techniques we used to use it in our diagnosis system. Like we used some cache counters as the indicators in the diagnosis. But in terms of whether we could use the prediction, I think in our current prototype, I think it's we haven't thought about it, but I think it will help us it will certainly give us more information and help us about what kind of problem we need to focus on, like because we have a lot of packets in this network function chain, and we need to focus for a significant problems among all these packets, all these problems. I think this prediction may be useful in that case.